Good afternoon and welcome to the 7th lecture of Eleng 16A, Module 2 Circuits. So today we still have a pretty full and interesting list of topics. We're going to finally build that capacitive touchscreen. We're also going to learn about one new component called a comparator. Fortunately, it's very simple. Even simpler than Ohm's law, simpler than resistors. So hopefully that will not cause any confusion. And then we will also talk about the energy that is stored in a capacitor. Okay? So sort of use, for example, to use a capacitor as a battery replacement. The other thing that I would like to say is that as you probably know, the midterm 2 is going to be Monday evening. Okay? And today is the last lecture that is in scope for midterm 2. So now I understand that sort of I shoot myself into the foot for my Thursday lecture that I very much hope that you attend because the material is not only on the final, but it's also very interesting. But anyways, you don't need to worry about anything in the lecture past today. Discussion tomorrow, we will still try our best to help you absorb and assimilate and understand and whatever you want to call it, the material taught up to and including today. Okay? So we will do our best, obviously, per use Piazza, per use office hours. I incidentally have an office hour just after this lecture. I will come. If you have any questions or suggest anything, you can come to that office hour. There are many other office hours. There again, discussion tomorrow. So please make use of all of that in order to clear up any questions that you might have. And of course also interrupt me during the lecture, but let's keep it more sort of to the topics of today's lecture. Are there any things that, any questions right now about that? Okay, everything's going to be clear. Everything's clear. The questions show up on the midterm, right? Okay, let's hope not. All right, so capacitance. We talked about capacitance last time we introduced that concept. And let's just remind ourselves what a capacitor is. In the simplest way, a capacitor is two conductors. So there could be a wire, conductor A, and a conductor B, and they are insulated from each other, so there is no wire between them or so. Okay? So then this simple contraption consisting of two conductors forms a capacitor. Any two conductors, if they're here, there is some. If I have some metal here, and you have some metal, maybe a ring or something, there is going to be a capacitance between the metal here, or maybe my glasses, I don't know whether they're metal, let's say they were metal, between my glasses and your ring. There would be capacitance. Obviously it's going to be very, very small, so we probably can neglect it. But it's just useful to realize and to understand that any two conductors, there is going to be capacitance between them, and we can measure it, and in some cases we can calculate it, and so on. Okay? So why did we just talk about this? Well, because we want to make that touch sensor. And this is again one of these design problems like we've run into from, I guess, the first lecture of Module 2. We want to build something. We want to build a capacitive touch sensor. I suppose, what is that? Well, it's some kind of a touch sensor, something that detects touch, and it uses capacitance to do that. Any ideas how we could go about this? And remember, we don't need to have a really clever idea. Just anything that sort of gets us going. We probably will find that it's not perfect, At least when I do design, I usually come up with really crummy ideas first. But then I look at why are they crummy, I make them a little bit better and so on. And sometimes, in the end, they come out to be pretty good. So let's try the same thing. Anybody has any idea of what we could do, how we could use capacitance to measure touch? Yes? Okay, so the idea is if you touch a screen, there would be somewhere conductors and they're close together, and if you put your finger there, you change some energy or so. Okay, well, so, I mean, that's certainly a great idea. Somehow we need to maybe go now a little bit further. We need to put where these conductors are and where the capacitor is, and in order to somehow make that a little bit. Let me give, any other ideas? Let me give you one idea. We could arrange two plates, just like this. That's a capacitor, right? In fact, if this was a parallel plate capacitor, then the capacitance would be equal to this epsilon times the area of the plates divided by the distance t between these plates. Right? So anybody has an idea on how we could use touch to change the value of this capacitor? Yes. Okay, so the idea is if we somehow use touch to bring these plates closer together, that is, reduce the value of t, the distance between the plates, well then the capacitance would increase and we ought to be able to detect that. All right? So that's a really great idea. It's a little bit similar to the resistive touch screen, right, where we also brought conductors together and then we detected that. Perfectly fine. Let's maybe actually try to do something that is slightly different in that nothing moves, right? One of the things about the resistive touch screen is you have to physically move it and the screen becomes a bit squishy, and I do not know that for sure, but I could imagine that maybe that was one of the reasons why more modern devices, they switched from resistive to capacitive touch screens. Yes, back there. Okay, so the idea would be we could use the finger as one plate of this capacitor. You had also an idea? No. Okay. So let's look at that. If we put the finger here, if we had a finger, well, I guess how would we do this? Maybe we would have a plane like that, sort of like a ground plane, a huge big conductor, right? So that would be, let's say, plate A of a capacitor. And now, on top of that, we put a material that is insulating. Glass, for example, is an insulator, and it works well on a touch screen with glass anyways, right? So there are various materials. There could be choices that would be insulated. So all of this is filled with this insulator thingy. And then we come with our finger. The finger is somewhere big like this. Okay? So this is the finger. Okay? Okay, and so now your colleague said something that's actually important. The finger is conductive. So what that basically means is that this layer here, the part of the finger that touches here, that's a conductor. That's a conductor. So actually, if we looked a little bit more into sort of the physics of fingers, then the skin, at least when it's dry, is actually a pretty good insulator. But inside the finger, of course, we have all sorts of fluids, and so and these fluids, they are filled with salt, various types of salt that the body uses to function. Right? It's not quite just water, and that makes it that it's conductive. Okay, so let me actually redraw this. Let's get rid of the finger, even though you find it extremely amusing, apparently. So from an electrical point of view, really all that matters is we have this conductor A, and then we have the insulator. I'm not going to draw this again, but then we also have the finger, and that's the conductor B. So it's really a finger, but this doesn't really matter. Okay. So now because of this arrangement, there is insulator in between these two plates. Well, these are two plates separated. We inherently form a capacitance C. That's just because of the way capacitance work. The minute we have two conductors, in between them we're going to have some capacitance. So as we bring our finger there, we get the capacitance. If we remove the finger, the capacitance is no longer there. So now, of course, we need to do something a little bit more to make a touchscreen out of this. What do we need to do next? We need to detect the capacitor, right? We somehow need to find perhaps the value or something like that of the capacitor, or the presence of the capacitor. How would you do that? Well, in general, if you want to detect any electrical element, what are you going to do in the lab? You're going to connect wires to it, right? So we're going to connect the wire here, A, and we're going to connect the wire here, B. Okay? And so we still need to figure out, once we have these wires there, what kind of an electrical circuit we're going to use in order to measure or detect the presence of this capacitance. But, I mean, let's just deal with the wires for the moment. Is it difficult to put the wire A? No, we have a plate there, it's conductive, we can solder it to it, or another clamp it to it, or glue it to it, whatever. Use conductive glue. What about the wire that goes to B? So we have a little bit the same problem as we had before. Initially, when we built that resistive touchscreen, we needed to have a wire that the person needed to take the wire with his hand and put the wire in various places. We weren't convinced that was a good idea. Unfortunately, we came up with a much better idea. So here also, we need a better idea. Anybody has an idea for a better idea? Okay, so let's. I mean, this is not so. It's like many of these things. If you brainstorm long enough, or if you see it, then it's sort of obvious. But let's again. We start with this conductor A, and now let's actually make outright a capacitor. So we put another conductor B here. So in terms of circuits, there are now two conductors. In between these two conductors, what do we get? Capacitance. Okay, so I draw it. I draw this capacitance. So I draw both the physical arrangement, black and green, and then I also, on top of that, in blue, draw the circuit, sort of the circuit representation of that physical contraption. Okay, so now, again, there is everything sort of insulator or so, and on top, we put now our finger. Let's call this conductor C. Again, this would be really the finger. Okay? Okay? So this is our finger, and this is a conductor, we just said. Okay? No fancy drawings for the finger. For what electronics is concerned, it's just a conductor. Okay? Right? And in between here, the white space actually insulator, but I'm not going to draw the insulator, otherwise my diagram gets too messy. Okay, now that we have this additional conductor, do we get new capacitors? Anybody sees a capacitor? Between which two nodes do we now have a capacitor where before there wasn't one? Between A and C. Yes. So there is actually a capacitor here between A and C. And we could also say that there is a capacitor here between A and C, on the left side, on the right side, right? We're going to get these capacitors. Can anybody see yet another capacitor that we're going to get also? A and B, right? So A and C. B and C. Okay, so you know what I mean. So let's call this one C0, this one C1. And C1 is present only if there is a finger present, and this one C2A and C2B. Okay, so now, how are we going to detect the presence of the finger? Well, let's start again with this question of where can we attach a wire? Well, apparently we can attach a wire here in B because there we made that conductor, right? And also A, we also made that conductor. What about C? No, that's the finger. We're not going to stick a wire to the finger. Hurts. Okay. So we have available these two nodes A and B, and between them we have all these capacitors. We have the capacitor C0, but then we have additional ones that are present only when there is a finger there also. So let's figure out what the capacitance between A and B is with and without finger. Okay? So without finger, no finger. Well, then we have node B and we have node A, and between them we have a capacitor, and the value of the capacitor is how much? Come on, I mean somebody needs to know. What is the capacitance between A and B? No finger, yes. C0, right? C0. And all the other capacitors, they are not there because the finger is not present. Okay? So now, let's draw the situation again, but this time with finger. Let's just draw these two electrodes, B and A. And we're going to have, of course, C0. And now, I would like everybody to stand on their head. Okay. But look, I mean, sometimes it helps to redraw a circuit because it's sort of funny that the capacitor C1 goes up and then it goes down through C2 and so on. It's hard to just see which one's in series, which one's in parallel and stuff like that. That's hard to see. So we are actually better off to redraw this diagram a little bit. Let's introduce the node C here in the middle. And then between B and C, well, we have a capacitor. So, and the capacitance of this in between there, we call that C1, right? You can now, once you draw it like this, you can easily see which capacitor goes where. And likewise between node A, why did I make A0 here? A. Between node A and C, we also have capacitors. There are C2A and C2B. So, and here we have another one, C2B. So that's with the finger. And this diagram, notice, is exactly the same as the diagram we had up above there. Okay? It's just redrawn a little bit. That makes it easier to see sort of series and parallel. Yes, you have a question. The question is, why are there two capacitors, C2A and C2B? Well, it has to do a little bit with capacitor physics, right? There is basically over here, we could have split this up into different conductors. Here there would be one piece that is one conductor, and here there is another one that is another capacitor, and then we can use the parallel plate capacitor equation and so on. But of course you're right, because everything's connected, then there is really just one capacitor. So both ways are correct. Okay? So now let's figure out what the capacitance is CAB. What do I mean with CAB? Well, it means the capacitance between nodes A and B. Well, in this particular case, without the finger, that's pretty easy, right? So in the other case, CAB now is going to be equal. First of all, we have two capacitors in parallel, C2A and C2B. What's the total capacitance? And they are in series with C1. So again, they are in series, but we use the parallel symbol. So now you know you have to multiply. So actually, why don't we do that quickly? Just to remind us how this works. 5 CAB, AB in that case, so that's this case, is going to be equal to C1 times C2A plus C2B divided by the sum of everything, C1 plus C2A plus C2B. Okay, so that would be the capacitance. Of course, we still have to go and figure out what is C1 and C2A and could use parallel plate capacitor equation also. Okay? So what we apparently, actually, let's say this, let's call this no, and this one phi. So there's capacitance no finger and capacitance finger, okay? Yes. I didn't hear. Oh, very good. Very good. Yes. So I made a big error. So plus C0. Yes, C0 we get in any case, and this one also plus C0. Thank you very much. Yes, I made a mistake. I totally forgot about C0. Other questions? Okay, so question here? If you voice your question, then we may be able to help you and clear something up that maybe, 20 other people also have a question about. No? Yes, back there. Well, we kind of are doing this, right? This equation, if I rewrite it, we could simply say that we define C2 as C2A plus C2B. Yeah? You agree? Now this is correct. Okay? And then you can write CAB finger is equal to C1, C2 over C1 plus C2 plus C0. Is that okay? No? We can do this. Yeah. Any other questions? Okay. So okay. So now I have a question. So we have the capacitance CAB no finger, and we also have the capacitance CAB with finger. Would you say that can you say one of these capacitors bigger than the other one? Yes, which one? The ones with the finger. So apparently what happens is we are always going to have some capacitance, C0, but the minute the finger is present, then we are going to have more capacitance. So the question apparently that now, the next question or the problem we have to deal with is we have to come up with a circuit that allows us to detect the size of or the value of a capacitor. Specifically a circuit that will be able to detect if the capacitance increases. Okay? So, well, how could we do that? Any ideas on that? Yeah, no, for something like that, it's perhaps helpful if we remind us of the characteristics of a capacitor. Right? There was the charge stored in a capacitor was equal to the capacitance, that's how capacitance is defined, times the voltage across the capacitor. And then we can do the differential. Incidentally, that's how I remember this equation. We differentiate with respect to time, so then we get dq dt is going to be the current running in the capacitor. Let's assume that C doesn't change with time. Let's assume this all along for our touchscreen. It's a little bit, kind of makes no sense because sometimes the finger is there and sometimes it's not there, and therefore the capacitance changes with time. But let's assume that we measure for a long time with the finger there, and then we measure for a long time with the finger not there, and so we did this as sort of two separate situations that, and we're not interested in the transition. Okay? So times dVc, which is a function of time now, dt. Okay? Okay, if we look at this equation, we have a value of a capacitor that we would like to know what it is. What could we do? What could we do? I mean, just like when we wanted to measure a resistor or a Thevenin open circuit voltage or a short circuit voltage, what did we do? Yeah, we applied some test signal to our circuit, and then we measured something else, right? That's how we do it. We apply some electrical thingy, and then we figure out some other thing that hopefully depends on what we are actually interested in. So in this particular case, apparently the electrical things we can apply to a capacitor are either current or voltage. And if we apply one, then the other one is going to change and vice versa. Okay? To me, it sounds a little bit easier to apply a current than to apply a voltage, because voltage we have to actually use a voltage that changes with time, whereas the current we are fine, right? We just need to apply that current. Okay, so let's use this following circuit. Let's have here our capacitor. So I just draw it like this. So that's the capacitor of CAB of our fingerprint sensor. We would like to know how big it is. Okay, so now we hook up a current source. Let's call this guy I0. Okay. And then we, of course, can now measure something else. For example, we can measure V of t. Okay? So in fact, if we solve the equation above, then we find that C unknown, or CAB, is equal to IC, or I0 now. Here we have used this I0, divided by dVc dt. Oh, wait a second. No, that's not what we want to observe. We put in a current, we want to observe the voltage, so what we really need is dVc dt is equal to IC over CAB, the unknown capacitance. So in other words, what does this equation tell us? Well, it tells us the voltage across the capacitor is going to change with time, and it changes with the slope that is equal to IC over C question mark. Okay? So we could integrate this, but we simply also can plot this. So let's do that. Let's plot this. We're gonna plot Vc, which is a function of time, as a function of time. And that's going to change. It's going to start at some initial value. Let's pick 0. And then it changes with the rate that is equal, a slope that is equal to dVc dt, and that happens to be IC over C question mark. Okay, so let's assume that this was C question mark. Here this was C question mark, CAB, no finger. What happens now to this graph if a finger is present? How would the graph look like if instead a finger had been there? Well, I0, does it change? No, that's our test current source that we somehow cooked up in the lab. It doesn't know that the finger suddenly is present. Well, then there is another choice. The capacitance C question mark. That one is now larger or smaller? It's going to be larger. And then the slope of this thing is going to be steeper or flatter? Flatter, right? Okay, so there's going to be a lower slope that corresponds to I0, actually here, I0 divided by C, A, B, finger. Okay? Okay, so this kind of is useful. We could start, we have to make sure that we always start in the same place, so make sure that the voltage across the capacitor initially is 0. We hook up that current source, and then we measure the voltage. Now, we have to, of course, measure it always at the same time, right? Because the voltage, even the red curve, if let's say your threshold was this much, to detect whether a finger is present or not. Well, if we wait for long enough, then with or without finger, we're going to get to this voltage. In fact, if we wait long enough, what voltage are we going to get? Infinite, right? It just keeps rising. So we'll have to deal with that also. Otherwise, we're going to zap the people using our touch screen or something. That would not be good. Okay, so we probably have to always measure at some time T1 or so. And then we have to determine is the voltage above or below that threshold, right? And then once we've done that, of course, now we know whether there is a finger present, then we want to again know is a finger present. We somehow have to discharge the capacitor. How would you do that? Yeah, short across it, put the wire across it or so, right? Then the voltage on that capacitor is 0. All the charges, they circled around in that wire. The energy is all dissipated. And then we do exactly the same experiment again. We wait for a time T1. We measure the voltage, check. Is it bigger or smaller than this threshold voltage? We perhaps determine in the lab what is the good value. And depending on that, we decide that, yep, green, we have no finger, or red, the voltage is smaller, or we must have a finger present there. Okay? Or a drop of water, by the way. It's conductive too. That's the reason why these capacitive touchscreens don't work very well in the rain. Yes, you have a question. So that we start here at the voltage 0 volts, right? When we do the experiment, when we start the experiment, then we need to start from a known place. If the red one started up here, if it was already charged and looked like this, well, then we would, of course, make a mistake. The voltage would always be large. Yeah? So, known point. Yes, Gireeja. Oh, okay. Yes. Thank you. No. We measure at the capacitor is. So the question was, how can you measure the voltage across the capacitor? So let's look at, for example, this diagram again. So the capacitor really is just two conductors. In this diagram, they're called A and B. Okay? And of course, now there is no wire that connects those together. We can go and attach a current source or so to do a measurement. Right? Does this answer your question? so we have this circuit here, right? So how could there be voltage? I'm not saying that there should be voltage across the wire. I'm not saying that we are looking at this V wire. This V wire, of course, would be zero. After all, we have a wire between these two nodes, so that's the whole point of the wire, that the voltage is zero. But we are looking at the voltage between this node, this plus, and this minus. And in between, we have a capacitor. Could also be a resistor, or could be a source, or anything like that. But we have a circuit element, and across the circuit element, of course, very much can we have a voltage. Unless that circuit element happens to be a short, we're going to have, likely actually going to have some voltage if the circuit is turned on. Okay? And the capacitor is not a short. Okay? Now, makes sense? Okay, thank you. Any other questions? Yes? So, the question is this always a straight line? Well, basically, the slope is dV CdT, right? And that happens to be equal to the current divided by the capacitance. So the current, we use some kind of, we'll actually design that next lecture, but we will use some kind of a contraption that puts out a constant current. It doesn't change all over the map all the time. We couldn't do anything useful with it, right? So the current is constant. What about the capacitance? Well, let's just assume that for the time for a measurement, the capacitance is also constant. So, in other words, we are going to put the finger there, leave it there. The capacitance now is fixed, right? Constant. Then we hook up the current, we discharge the capacitor, we hook up the current source, we make our measurement. The capacitance is constant, and we make this determination, is the finger present or not. Once we're done with it, we start the whole process again. Now the value of the capacitor could be different because the person may have lifted the finger or left it there, right? So to answer your question, yes, under those circumstances, if neither I0 nor the capacitor changes, then the slope is constant, and yes, it's a straight line. Make sense? Okay. Any other questions? You're back there. Oh, can somebody else explain it? I'll tell you why. Because my brain is wired in a certain way. And what I sometimes feel is that your brain is wired slightly different. And so if I just repeat the same thing, it makes just utterly no sense again. So could somebody else explain it? Why is the green one and why is the red one? Why is it straight line? Yes. Thank you. Did you hear that? Okay. Fine, thank you. Yeah, so I guess your colleague said it in many fewer words than I used, so see, our brains are wired different. Okay, so, all right, so we have a process that sort of works, right? So how I mean, if you again summarize, so you would tell the person, either now put your finger there or don't put it there, okay? Fine. You have decided whether your finger should be there or not? Okay, fine. Now, let me first put the short across the capacitor so it's discharged. Then I put that current source. Then I wait for time t1 and I use my voltmeter to measure either this or that point. Okay, I mean, I think that's what electronics is for, right? We're not going to go and muck around with our circuit all the time. So let's sort of fix this up a little bit to make it a bit better. So one of the problems is that the voltage once we start, the voltage keeps increasing, right? So it would be nice if the voltage after a certain time started decreasing again, because otherwise, I mean, we're going to get to an infinite amount of volts and so on, and something's not going to go right. Okay, so let's come up with an idea of how could he make it that right now the slope is positive, it keeps increasing the voltage. How could he make it that the voltage goes down? In other words, the slope is negative. What? Okay, yes, a very good idea. If the sign of the current would change, well, then the sign of the slope dVc/dt would change also. So basically, what we are going to do is, as a function of time, if we plot it here I0, it's no longer constant. It's going to do something like this. And then after some time, it's going to be negative, and then it's going to be positive again and negative again. Okay? And now here again we have Vc of t. So now the voltage, of course, is going to increase as long as the current is positive. And then when the current goes negative, it's going to decrease like this. And if the capacitance was larger, then the same thing would happen, except that it doesn't increase quite as much. Huh? Okay? How about that? Does it go? Should we try this? Is it worth running to the lab? And yes. Okay, so the question is, what if here there is no finger, and then suddenly here there is a finger? The slopes would be different, we wouldn't end up at 0. Okay, you know, that's a very good question. I can tell you that I went to the tape of the spring lecture, and I thought, well, that's a good question. How this doesn't work, right? And I couldn't find anything in that lecture whatsoever. And then I went to the circuit diagram for what you're actually building in the lab, and I found a slight difference that makes it that it works. So, I do not want to confuse you today just before the midterm, okay? So we're going to simply ignore this problem, a very important problem, okay? We're going to simply ignore it. And I promise that when the fog has a little bit cleared, then I'll tell you how we're going to deal with this problem, okay? Is it a deal? Okay, so let's keep things simple and just assume that this wasn't a problem. But you're absolutely right. So, okay, so now we have again this threshold. Let's put the threshold somewhere here. And let's just plot the value of, basically, let's call this VTH. And here we plot, okay, so now I need a hover hand. Okay, so what we are going to plot here is Vc of t greater VTH. Okay, still as a function of time. So that's basically going to be here. And it's not going to be over there. So in other words, here, if we plot this, let's say we could plot this as a 1 and a 0 here. Then we are going to get something like this. When there is when there is no finger, we get this condition, this inequality, we get that met for a brief period of time. Right? And then afterwards over here, with finger, now I think I know which button at least to press. Okay, when a finger is present, then we don't get that blimp. So we somehow could hook this up, for example, to an LED, right? This output 0, 1, 0 volts and 5 volts, could hook it up with an LED, don't forget the resistor. I think you built a circuit. Anyways, and then the LED would be lit whenever there is no finger, and the minute you put a finger there, the LED would turn off. Okay? Looks like a pretty decent circuit. There is one little thingy that is left to do. One little problem. And that is the black thing. The black thing needs to be some kind of a circuit, right? We want to not go and do math or so. We want that our circuit does all of this. And for that, we're going to use a comparator. So I promised that this was a simple element, so let's see. A comparator. So comparator is a new circuit element, and this is the symbol. It has two terminals at the input, and the output is going to be either of one of two voltages. So in fact, you apply to it the supply. Usually the supply is called VDD, whatever. And you also apply a negative supply, VSS. That could be just ground. That would work fine. It could also be minus 5 volts, whatever, okay? It has these two terminals, and you hook them up. And it has two inputs. One input is V plus, and the other input is V minus, and it has an output, V comparator. And that output is going to be equal to that terminal. The output is going to be equal to VDD if V plus is greater than V minus and VSS otherwise. Okay? So when you see a circuit element like this one, the symbol looks a bit more complicated than our resistors or so, but the function is very, very simple, and it's described by this equation. Okay? So that's all you need. Yes. How do these elements work? Oh, this is another wonderful question that, there is this course 240B, and we built this. Okay, so there is a little bit more to that. Start by taking 105. Or you can also come to my office hours and we'll talk a little bit about it. But this one turns out to be harder to explain than the A to D converter. Yes? Difference between V plus and VDD? Oh, there are simply two different voltages. Just like what's the difference between 5 volt and 10 volt or so? You can have lots of different batteries, right? So VDD and VSS, that generally would be the supply. You hook it up to your battery, the VDD, and VSS, maybe you hook it up to ground, the negative terminal of the battery. V plus and V minus, well, in this circuit here, that would be VTH here, and this would be VC of T. Okay? So now you have 4 different voltages. Yeah, good question. Okay? Any more questions? Yes. So the question is there any relationship between VDD and V plus or between V minus and VSS? For an ideal comparator, there is no such relationship whatsoever. Okay? For a practical comparator, there may well be. In fact, in the lab, you're going to use one. Okay? And for that, there are some limits. For example, you couldn't put 1,000 volts on it anyways or so, right? Real components, they do have some such limitations. But this is not going to be a big problem, okay? Okay, so while you think about more questions, I'll set up a little demo. Does this actually work? So, I have, maybe I should explain what I have. Huh? So I have a little circuit here. It's again a little microcontroller. Oh, that was a bit too much. Okay, so there is a microcontroller here, but more interestingly, there are 4 touch sensors. They are round. I mean, hey, I like round. So there is also an audio synthesizer. This is an amplifier. We're not going to use it for this. So anyways, I need to apply power and then nothing happens. But now, the demo is not the most exciting demo, but anyways, I can press one of these capacitive touch sensors, and then the corresponding LED lights up. So for 1, we have apparently red. For 2, we get green. It's a multicolor LED. For 3, we get blue. And for 4, we get white. And then we can, what is it if I press 2? It's going to be green. And, I can make sort of a light show. Okay? So, but anyways, it's a capacitive touch sensor. If you don't believe me, you can at least look at the demo afterwards, but this is the little board. You can send this through class to, I don't know, to have something to look at. Okay, so such touch sensors, they work very, very well. Capacitive touch sensors work very well. There is still quite a bunch of stuff to do. Current source. Okay. We have to figure out how to build a current source, right? We have to, what else? We have to deal with your problem there. Well, I don't even know how to call it, but I won't forget. I have it in my notes, but not today. And what else? We need to scale. Basically, so far we made touch sensors that detected a finger or not. Ultimately, we want to have an entire touch screen that has lots of touch sensors so we can detect where on the screen the finger is, or perhaps not. Okay? So we have to still deal with these, and again, there is this problem that we will have to deal with. So, but let's keep that for after the midterm. All right? Okay. So with that, let's move on to another topic. So, when we look at the capacitor, let's say we had a current source like this, some I0, and we connect a capacitor across it, then we get the voltage Vc of t across it, and that's going to be, if the current source is constant, as a function of time, it's going to look something like this. This current I0, of course, is going to flow into the capacitor. And so how much power goes into the capacitor? Well, the power that flows into capacitor P, C, as a function of time, is going to be just like for any, it could be a resistor or anything like that, it's going to be the voltage times the current. So it's going to be Vc of t times I0. Okay? So the power, so that's Vc of t, and P of t actually does exactly the same thing. The power that flows to the capacitor increases. Initially it's 0 if the voltage across the capacitor is 0 because it's voltage times current, right? So the power is 0, and then it increases linearly again if we don't change the current or the capacitance. Okay? So same deal as before. Okay, so so let's figure out how much capacitance, how much power goes to the capacitor, so that Vc of t, dVc of t is going to be equal to I0 times I0 divided by c times dt. That's basic from dVc dt equals I0 over c, right? So now we integrate, so we get Vc of t is going to be equal to I0 over c. We assume that these are constant times t. That's simply integration. And now we can write again Pc of t is equal to I0 over c times I0 times t. I substituted from up here. So we're going to get, so now we have this, we have the power. Now let's figure out how much energy goes into the capacitor. Yes. So the question is, does current flow across the capacitor? The physics is a little bit odd in that electrons flow to the top plate. They're not going to somehow hop to the other plate, okay? But electrons are going to leave the bottom plate, okay? So there are lots of electrons, right, if you have a metal like copper, it's filled with electrons. So you can also remove some. Yes. You're absolutely right. The question is, when I do this integral, do I not have to add an initial condition? Yes. I set the initial condition to 0, but you're absolutely right. I'm not mathematically accurate. Okay? Yeah. So now we want to know the energy. Well, what is energy? Energy is the integral of power with respect to time. Okay? So apparently the energy delivered to our capacitor is equal to I0 squared over c times the integral from 0 to t dt, and that is equal, assuming the capacitor was discharged initially, so the energy on the capacitor 0 is going to be equal to I0 squared over c times t squared times 1/2, t squared over 2. Okay? So this by the way, on the midterm, you're not required to do such integration stuff like that or so. You will finish this result, then just put that result on your cheat sheet and be done with it. Or you can put it also in your memory. Okay? So let's rewrite this a little bit. Let's write this as I0 times t squared divided by c times 1/2. Okay? This is identical, right? I mean, it's just... So, but now, what is I0 times t? Well, charge is the integral of current. So I0 times t is simply the charge that I delivered to the capacitor. If the capacitor was initially discharged, this is precisely the amount of charge that is now on the capacitor. So, did I do this right? Okay, so we get the charge squared divided by capacitance times 1/2. So that's the charge on the capacitor. Let's make this the capacitance squared, and I put another c here in order to fix my change. Okay? So charge divided by capacitance, well, what is that? So Q equals C times V. So Q divided by C is equal to V. So apparently this is equal to 1/2 C, that's this C, V, that's now this V, there, okay. So the energy stored on a capacitor is equal to 1/2 the value of the capacitor. So bigger capacitor, you can store more energy on it, okay? Times the voltage across the capacitor squared. So if you have a capacitor on your bench, has 1 volt across it, you measure that with the voltmeter or so, has 1 farad capacitance, well then it's 1 times 1 squared divided by 2, 0.5. What's the unit of energy? Joules or watt seconds, okay? So you can figure out that quite easily. We have another 5 minutes or so. Let me try to make a little example. We may not get all the way through, but at least we get the idea of it. So we could use if a capacitor can store energy. It basically does a little bit the same thing as a battery. A battery also stores energy, and then afterwards you use the battery to power some gizmo with it. Well, we should be able to use a capacitor to do the same thing, right? Why would you ever want to do this? Well, one of the reasons is that charging capacitors takes a lot of time, right? You must have noticed that. Charging batteries can take a lot of time. Yeah, you notice that. Your phone is dead. You plug it in. Well, it's charging. And a few hours later, finally it's charged. With the capacitor, you simply connect it to a 5-volt source and boop, it's charged to 5 volt. What's the energy on the capacitor? Well, it's this much. So it can happen very, very quickly. And there are applications where that's important. For example, if a little toy, a little airplane or so, it flies for a little bit and then it runs out and you want to charge it again. Right? You don't want to wait 3 hours before, with your kid or whatever, before you can fly the airplane again. You want to charge it instantaneously. Another important application is in cars. Electric cars, they have batteries, and there it's a little bit the opposite. You don't necessarily want to charge very quickly, but that would be nice too. But that would be too expensive to use capacitors in a car. But you want to be able to suck out a lot of energy very quickly. If you want to start at a green light and you want to start very quickly, then suddenly you need 1,000 amps or something like that. Well, the battery turns out has a hard time delivering all this big current. So you put a capacitor and then while you're starting, it discharges the capacitor, uses that to jump start the car, and then afterwards when you're cruising, the battery recharges the capacitor and runs the motor and so on. It works just fine. Okay? So there are lots of reasons why you would like to do this. So let's say that we had a capacitor and we charged it somehow to an appropriate voltage and therefore an appropriate energy. And now we want to power a thing. So let's say that the thing that we want to power with it, what did I must have. I said it's just some kind of a robot. Whatever, it doesn't really matter what it is. So this is a current I load. So let's say your current draws a constant current I load equals 0.1 amps. It just uses that much to do whatever it's saying. Okay? So the capacitor is initially charged to a voltage V0, and then this current is going to flow, and the voltage on the capacitor is going to decrease. So we're going to have a situation that looks more or less like this. Time, here's the voltage Vc of t. I shouldn't have put V0 here. So it starts at V0, and then it's going to decrease over time. Well, why is it going to decrease? Well, because we're pulling current out of our capacitor, and the slope of this is going to be equal to well, the more current we pull out, it's going to be the slope is going to be steeper. And the more capacitance we have, well, the slope is going to be less. So dVc dt, and passive sign convention. Oops. See the current, the IC is equal to minus IL. So we need a minus here. Okay? Okay? So apparently what's going to happen, we charge our capacitor to a voltage V0. Everything fine. Then we start pulling current. We model our robot that uses that current, 0.1 amp. We model it with the current source. That's just for convenience. We don't want to design a robot also in 5 minutes left in the class for today. Okay? And so the voltage across the capacitor is now going to decrease. Well, why? Well, because we are sucking charges out of the capacitor and also energy out of the capacitor. Okay? So at some point, the robot says, that's enough. I'm going to quit because the voltage now is too small. I cannot run anymore, okay? So now, what we could do, and maybe that we can still try to do in 5 minutes, we could try to calculate how big a capacitor do we need so our robot can run for a certain time, right? Okay? So let's say that with this V0, for example, was 10 volts, and the V-stop was 6 volts, and we want this to be, let's say, 40 seconds. You can put other numbers if you like, different numbers better. Let's calculate what this is, okay? And IL we already have is 0.1 amps. So the voltage on our capacitor is going to be equal to V0 minus dVc dt. or if, actually plus dVc dt, so that's going to be equal to V0 minus C over IL, okay, times T. Okay, so we're discharging the capacitor with the current IL, so the voltage across the capacitor is going to decrease. So these, yes. So the if current runs out of the capacitor like this, the voltage across the capacitor is going to decrease, right? So there must be a minus sign there. Okay. So you define. Well, I have defined IL as a positive current. Oh, yes. Yes, yeah, you're right. Thank you. It was always like this. You didn't look right. Okay, thank you. I make mistakes, obviously. Okay, thank you. So you saved me. So V stop is equal to V0 minus IL over C times T stop. And now we can solve this for T stop. Another example why equations are. Well, actually, T stop we're not even interested in. Let's solve this for C. C is going to be equal to T stop over V0 minus V stop times IL. Okay. I wrote this down because otherwise I make another stupid mistake in front of you. Okay, so T stop was 40 seconds. We want to run this for 40 seconds. V0 was 10 volts minus V stop was 6 volts, so that's 4 volts. And IL was 0.1 amps. So this comes out to be 1 farad. Okay, we need a 1 farad capacitor. Turns out these capacitors are pretty big. 1 farad is a huge capacitor, and therefore it has a fitting name. This is called a supercapacitor. And you can buy those up to about maybe 10 farad. If you want more, then you need to put them in parallel. Okay. Are there questions about this? Yes. So, why is it? How do they get this in the first place? I always start with this. Then take the derivative. C is equal to dV dt. Okay, dCVT. So then dVc dt is going to be equal to IC over C. Okay, but now actually I would like to tell you something that was going to help you on the midterm, I hope. And that is that if you see such an equation, you can ask yourself, what do I expect? If I suck out a lot of current, if IC is very big, would I expect that the voltage across the capacitor, is it going to decrease fast or is it going to decrease slowly if I pull a lot of current? Well, at the extreme case, if IC was 0, I would expect that the voltage doesn't change at all, right? Because now I haven't really done anything to my capacitor. It's sitting there, so where would charge go? So the voltage should stay the same. So I would expect that small current means small d dVc dt. Large current means large dC dt. Likewise about the capacitance. If I have a really big capacitor and I'm drawing a little current from it, do you think the voltage is going to change rapidly or slowly, right? Because it's a huge capacitor. You need to suck out a lot of charges for the voltage to even start changing. Okay, so when you get a result on the midterm, you get a result like this one, you derive this and so on, and it was hot in the room and whatever, you're even maybe nervous, I hope not. Then look at the result and ask yourself, does this make sense? Here I didn't do that, right? I should have said, well, if I have a bigger capacitor, why would the voltage go down quickly? Makes no sense, right? So if you do that kind of thing, you can catch errors easily. You don't need to redo your calculation, make the mistake again. Use this sort of insight. Okay, see you Thursday, and hopefully in the office hour, some of you.
When you're at that board, the touch board, and you press one of the buttons, why is it when you let go that the lights stayed on?
It's because the microcontroller actually detects the touch and it stores that.
It just stays.
Yeah.
So if you were to click it again, would it turn off?
No, it's a program that does it.
Mm-hmm.